All right, so let's keep going here. Like that's not me. No, boron trifluoride in here. All right. So we're talking about these transition metal complexes, right? And so we would have learned to look at this formula here and be able to tell that the oxidation number of this transition metal would be +2, right? And then based on where it lives on the periodic table, we would be able to tell that its electron configuration is argon plus 6 3d electrons. All right, and that is by memory, so let me just double check that I'm not full of it. Excellent, okay. All right. We would have also learned that the coordination number of this complex is 6, which means that it is a geometry that is octahedral. Right? And that was really what we incorporated last time, is the geometry of these complexes. It turns out that when you take this iron 2 ion and you decorate it with these 6 ligands, when we have iron all by itself, right? So this would be iron alone, or yeah. All of those 3d orbitals are in the same energy level, all right? So if we were to fill this in with our 6 electrons, we go through and half fill first and then double up, right? That would be if you had an iron ion all by itself. But what we learned is that when we take these complexes, when we take those 6 ligands, this leads to a splitting of these orbitals, okay? So our 3d orbital splits in energy. When we have those 6 ligands around, right? Some of these orbitals are now higher in energy because of the presence of these ligands compared to others. All right? The difference here, that was terrible. We called that crystal field splitting energy, delta. All right, so as soon as we take that transition metal and we make it into a complex, an octahedral complex like we have here, it's going to lead to a splitting in those 3d orbitals where now some are higher energy than others. All right, and so now we need to fill in this diagram with our 6 electrons. In order to do that correctly, we got to look at which type of ligand we have, because our ligands are broken into 2 categories here. All right, they're really ranked. This is the smallest crystal field splitting energy over here, and this is the largest crystal field splitting energy. And there's this cutoff right here between water and ammonia, where these are considered high spin ligands, and these are considered low spin ligands. All right, and that's going to dictate how we fill in that diagram, because for high spin, we're going to half fill all orbitals first. Whereas if it's low spin, we're going to fully fill the lowest energy first. Okay, so water is a high spin ligand. So when I take my diagram here and I start filling it in with electrons, I'm going to half fill all my orbitals first, then I'll go back and double up. All right, so this is for this octahedral complex here. if I took this same complex, but I went in and I replaced all the waters with these cyano groups, I still have my iron 2 ion because the charge of each cyano group is -1, so I'd still get the same oxidation number. I still have 6 ligands, so it's an octahedral. So I'm going to use my octahedral splitting pattern. Okay. Let me get rid of these electrons because we haven't filled it in yet. All right, but with my cyano group here, should that crystal field splitting energy be larger or smaller than with water? This is the largest delta that we're going to see is for our cyano group here. So what that means is if I'm kind of going to visually represent it, now all of a sudden the difference in energy between these two is much greater, a much larger delta for this complex here. Let me just make room, kind of move it up. And because of that, when we fill it in, we're going to fill it in as a low spin complex where we fully fill everything on the lowest energy first. Fully fill these lowest energy orbitals first, and then if there's anything left over, we double up. In this case, we get rid of all 6 of them, fully filling those lowest energy orbitals. All right, so same transition metal ion. The difference is water's a high spin ligand, so I half filled all my orbitals. The cyano group has a much larger delta, a much larger crystal field splitting energy. And because of that, when I go to fill it in, I'm going to only fill in the lowest energy orbitals first. Then if they're all full, I'd move on to the next ones. All right. So again, we have this diagram for the iron ion all by itself. The iron ion paired with 6 high spin ligands and the iron ion paired with 6 low spin ligands, right? These are my different orbitals here. All right, and we said that these crystal field theories, they help explain the magnetic properties of these complexes. Okay, so when I say the magnetic properties, really that's code for number of unpaired electrons. All right, so I need to be able to fill in those diagrams so I can determine how many unpaired electrons there are in each complex. It turns out that when you have a magnetic field, something that responds to a magnetic field is responding to that magnetic field because it contains unpaired electrons. Right? So when you can stick a magnet to your refrigerator door, it's because the metal in your refrigerator door has a bunch of unpaired electrons associated with it. Okay? So in this case, if I were looking at my water complex, how many unpaired electrons do I have for that complex? 1, 2, 3, 4 unpaired electrons. And what about if I take that same ion, but now I'm going to make a complex with these cyano groups? How many unpaired electrons do I have there? 0. Right, so both of these complexes have this iron 2 ion in them. One of them's paired with water, the other with these cyano groups. And because of that, they have completely different magnetic properties, right? The water complex will respond to a magnetic field because it's got those 4 unpaired electrons. The other one's completely unresponsive to a magnetic field because it's got 0 unpaired electrons, okay? So again, this crystal field splitting theory, this idea that these d orbitals split when you put ligands around them, They help explain the magnetic properties of these complexes. Okay? The other thing we said is that they help explain the color of these complexes. All right? So let's say that I told you absorbs 450 nanometer photons. What color would we observe? All right, we're going to go to our little color wheel here. Okay, we said it absorbs at 450 nanometers. So that's right, yeah, probably like right about here. Okay. So then what is observed? The complementary color, right? So the thing on the opposite side of the wheel, if this is what's absorbed, over here is what's observed. So absolutely, we would observe an orange complex. Okay. So what is observed? Orange. All right. We also talked about how we could actually calculate, given this information, right, we could actually calculate that crystal field splitting energy because it's just equal to the energy of that photon, which would then be hc over that wavelength lambda. What's up? Lambda's in whatever units you're given. However, in the visible spectrum, nanometers is the most convenient unit to use. But you'll be given the units of lambda. All right, so then let's look at our similar complex here. I'm going to take that same iron ion, but this time we're going to pair it with these 6 cyano groups. And we want to know what color would we expect to observe from this complex here. All right. Now, obviously, if I gave you a wavelength, it'd be really easy to look on that wheel and figure it out. But here I haven't given you that information. I told you what it was for the water complex, 450 nanometers. But now I'm just giving you this formula here. So how are we going to figure this out? All right. What do we know about the crystal field splitting energy of my cyano complex versus my water complex? It's larger, right? If we look at our spectrochemical series here, the largest crystal field splitting energy is over here for my cyano group, compared to water, which is further down on that spectrum. So my crystal field splitting energy for this cyano is going to be greater than that for water. If we look at this equation here, delta is equal to hc over lambda. So if the crystal field splitting energy is larger, what does that mean about lambda? Is lambda going to be larger or smaller for these cyano groups? Smaller, awesome. They're inversely proportional. So that means my wavelength for the cyano complex has to be less than that for water. All right, so our wavelength of absorption is smaller because that crystal field splitting energy is larger. right? And lambda and delta are inversely related. Okay, so if I look at my color wheel here, the bottom line is if this is where my water complex absorbs, my cyano complex has to absorb somewhere in this region here, somewhere at a smaller wavelength. Right, so FeCN. All right, and I can't determine exactly what wavelength it absorbs at. There's not enough information there. All I can say is that it's going to be less than 450. So it's either going to be orange or probably more likely yellow, right? Those are the only two possibilities there. Everything else would be absorbing at a higher wavelength. So I can't definitively say, but what color can we expect? You can say orange or yellow. And yellow might be even more likely because we were pretty close to the edge of that orange region. All right, but that's really all I can say definitively, is that it's going to absorb at a smaller wavelength than our other complex. All right, so again, that crystal field splitting theory, the idea, this is the whole shtick of the theory, the idea that you take these metal ions and you decorate them with ligands, and that leads to a splitting in energy of those d orbitals. Okay, that one piece then helps to explain the magnetic properties of these complexes as well as the different colors that we observe. All right, cool. So when your coordination number is 6, you always have this octahedral geometry. All right, there's two other geometries that we're going to talk about. All right, and the other two that we're going to focus on are the coordination number of 4 complexes, tetrahedrals, and square planars. Okay, and both of these have this coordination number of 4. We'll talk about how we distinguish between the two here in a second. All right, we're going to focus first on the tetrahedrals. All right, let me just look at a periodic table real quick. Try not to pick the same examples 100 times. All right, so everybody take a second. We need to know the oxidation number. From there, we can find the electron configuration. And the coordination number. These are all 3 pieces of information you should be able to tell me just based on this complex formula right here. All right, and I will tell you, it's on our constants page, but just to keep everything here, these cyano groups each have a charge of -1. All right, so since I have 4 of these cyano groups, each one has a charge of -1. That means that my cobalt ion charge, my oxidation number must be +2. If I do my electron configuration for the cobalt-2 iron, that's the same as argon plus 7 3d electrons. Right, and my coordination number is 4 because that's how many ligands I got on there. All right, so again, for right now, you're just going to trust me that this is a tetrahedral, and I'll explain how I distinguish between tetrahedral and square planar here in a second. All right, but this is now a tetrahedral complex. Okay, and with our tetrahedral, what we want to note about this geometry is that we have 4 ligands, as we discussed, but a tetrahedral is how you orient all 4 of these ligands in space such that they're all equally spread out, right? There's the same amount of distance between all these ligands. If you guys ever worked with one of these model kits and built a tetrahedral, you can kind of take it and flip it around, and no matter which way it lands, it looks the same because it's all super symmetric. All right, so 4 ligands, all equally spaced. All right, so similar to what we saw before, if we take the cobalt ion, this cobalt-2 ion all by itself, those 3d orbitals are all sitting at equal energy. Okay. My electron configuration, 3d7. So I could fill this in with these 7 electrons. Remember, we half fill first and then go back and double up. So that would be the electron configuration diagram for the cobalt ion all by itself. Right? But as soon as we make it a cobalt complex, we see this splitting occur. All right, and then the splitting pattern for a tetrahedral, if we look on our constants page, is basically the reverse of an octahedral. Now I have 3 high energy orbitals and 2 low energy orbitals. So just like we saw with our octahedral, this is going to lead to a splitting, but because it's a tetrahedral, my splitting pattern is a little different. Now I have 3 orbitals up at the top and 2 below. Right, so this is the tetrahedral splitting pattern. Okay, so again, because this is a tetrahedral, I know which splitting pattern to use. All right, now I got to fill this in with electrons. The thing about tetrahedral is actually a little bit easier to deal with. Because there are only 4 ligands, right? There's not 6 of them, there's only 4 ligands. And all 4 of those ligands are perfectly distributed in space. The crystal field splitting energy is always much smaller for tetrahedrals, and they will always be high spin. All right, so given that this is high spin, everybody take a minute and fill in this diagram. Remember, what the heck does it mean to be high spin? All right. right? And so really what I could ask and what you want to be able to answer by filling this in is how many unpaired electrons? Correct, right. So that only pertains to the octahedral complexes. All tetrahedrals, regardless of ligand, are high spin, and it's because there are fewer ligands and they're all equally distributed. So you just don't have as much splitting going on in a tetrahedral compared to an octahedral. But yes, regardless of the ligand identity in tetrahedrals, it's always high spin. All right, so how many unpaired electrons? 3. Awesome. So remember what high spin means. It means I'm going to go through and half fill all those orbitals first. So I got 7 electrons to put down. 1, 2, 3, 4, 5. Now I'll go back and double up. 6, 7. So indeed there are 3 unpaired electrons in this complex. Okay? And again, what we got to remember is tetrahedral is always high spin regardless of what ligand you use. Okay? Let me real quick. All right, so now let's do our last one here. Before we get started, you got to give me that electron configuration for the following complex. So this would be the copper 3 ion, which means that we got our argon's electron configuration plus 8 d electrons. All right, and so for right now, you're just going to trust me that this is a square planar. All right, if we just look at a square planar real quick in contrast, we also have 4 ligands, right? So my coordination number is 4. But now these 4 ligands are not equally distributed. They are all clustered around that center. Okay? So unlike our tetrahedral, we do not have this equal distribution of ligands. We have these 4 ligands clustered around that central ion. All right, if we had copper alone, those 3d orbitals would all be at the same energy level. So I'd fill them in. 1, 2, 3, 4, 5, 6, 7, 8. Who can guess what's going to happen to the energy of those d orbitals as soon as I put those ligands around? Is it going to stay the same? No, it's going to split, right? And for this, we got to look up our splitting pattern for a square planar, which is quite different. More of like a little totem pole staircase here, right? I got 2 low energies on the bottom, and then another one, and another one, right? So I have these 4 different tiers going on. Again, 2 at the bottom, and then boom, boom, boom. All right, so now we got to fill in these orbitals here, this diagram. We got to know whether we're filling it in a low spin or a high spin manner. All right, and for square planar, it's going to be always low spin. All right, those ligands are not evenly distributed. They're kind of clustered in this particular area. Higher energy, higher splitting energy, so always going to be filled in as a low spin complex. All right, so remember what it means to be low spin is you're going to fully fill lower energy orbitals before moving up, right? So I'm going to go 1, 2, 3, 4. Now I'll move up to the next level, 5, 6. Now I'll move up to the next level, 7, 8. All right. So if we have a tetrahedral, again, we're going to see this splitting pattern, but it's going to be different than we saw for octahedral. We have 3 high energy, 2 low energy. For these tetrahedrals, we always fill it in like a high spin complex. For square planars, we again see this splitting, but we're going to use the square planar splitting pattern. And we're going to fill these in with our electrons, but again, square planars are always low spin. All right, now both of these are complexes with a coordination number of 4, so how the heck do I distinguish between them? Turns out that D8 complexes prefer the square planar geometry. If you got 8 electrons in the d orbital and a coordination number of 4, it's square planar. Any other number of electrons will prefer a tetrahedral. Okay, so how did I know that this was going to be a square planar? Because when I did my electron configuration, it was 3d8. And again, the d8 complexes are square planar. Correct. You always got 8, right? So you can only fill them in that way. Yep. All right, and this isn't 100% true, but it's a great rule of thumb, and we're just going to stick with it. We're not going to learn about a bunch of exceptions to the rule or anything like that. All right, so if you have a coordination number of 4 and 8 d electrons, that's a square planar. If you have a coordination number of 4 and any other number than 8, that's a tetrahedral. Okay, but that d8 is how we're going to recognize square planar. All right, so now let's practice this crystal field splitting business. look at a periodic table real quick. All right. All right, so what I'm going to do is kind of take away these notes here to give it to you how it would be on an exam. We won't need the color wheel, so I'm going to focus here. Okay, and what I want to know is how many unpaired electrons in the following complexes. All right, and in order to answer this, you're going to have to go the whole 9 yards and build your crystal field splitting diagram and fill it in with the electrons correctly. All right, so everybody take a second and see if you can't determine how many unpaired electrons there are in these two complexes. NH3, good call, is neutral. Yeah. Nope, it's a neutral ligand. H2O is neutral, right? There's no charge on that. So if there's a charge, it's written for your ligand, right? We also have our other reference sheet as well, but it's always going to be written. But no, water's neutral, ammonia is neutral. Those are always going to be neutral. Ethylene diamine was also neutral. Yeah, so, okay, so just real quick. The charges are all written for all of your ligands, right? This is going to be on your constants page, so it's not any sort of a guesswork. It's always written in the formula. All right, so let's go through this real quick. So on the one hand, it's not too bad. It's just that there are like a lot of moving parts, and you got to get each part or you're screwed putting them together, right? So the first step is we got to be able to figure out how many electrons we have to even put in the diagram, right? So we need to be able to figure out our electron configuration. My oxidation number of my palladium in both of these cases is 4 because ammonia is a neutral ligand. So PD plus 4. If I look at my periodic table, my electron configuration would be krypton plus 6 4d electrons. All right, so that's how many electrons I'm going to be filling into my diagram here. If I look at this first complex with these 6 ligands, what would my geometry be? Octahedral. So this is my diagram here that I'm going to be filling in with electrons. All right? And again, how many electrons am I going to fill in here? 6, because that's what I got from my electron configuration. All right? And then when I fill these in, am I going to fill them in like a low spin or a high spin filling?
Low spin.
Low spin, right? So over here, these are our low spin ligands. Over here, these are our high spin ligands. I know that it may seem a little backwards because low spin actually means that the delta is large, whereas high spin means that the delta is small. Okay, but so I'm going to fill this pattern in, this octahedral splitting pattern in with 6 electrons in a low spin. So I'm going to go 1, 2, 3, 4, 5, 6. So how many unpaired electrons do I have in this complex? 0. All right, so now for the next one, I didn't change the metal ion, so I still have my palladium with this 6 4d electrons, okay? But now my coordination number is 4. All right, so I'm either going to be tetrahedral or square planar. And which one am I going to pick? Tetrahedral. Why? Because it's not 3D or it's not D8, right? If it's D8, you pick square planar. Anything else would be tetrahedral. So this is a tetrahedral. All right, and then I'm going to fill this diagram in. Am I going to fill it in high spin or low spin?
High spin.
Why high spin? Ammonia's over here. Because tetrahedral is always high spin. All right, so now I'm going to go 1, 2, 3, 4, 5, 6. And so I have how many unpaired electrons? 4. All right, so we could just note this spectrochemical series here. We only have to pay attention to this for our octahedrals. Cool.